At this point, we're going to see if we can use the minimal path sets to write any coherent system of n components as the parallel arrangement of series subsystems. To do this, we're going to begin by letting P1, P2 through PS be the S minimal path sets for the coherent systems. Even though it's not clear right away while we're defining alpha j of x in this fashion, here will be its definition. Alpha sub j of x will be 1 if all of the components of a particular minimal path set P sub j are functioning, and it will be 0 otherwise. Now when you see the words all components are functioning, that should make you think of a series system. And because of the relationship with a series system, you can write alpha sub j of x much more compactly as a product, and that's what you have right here. So our purpose is to write the structure function in the following fashion. We are going to let phi of x be 1 if all of the components of one or more of the minimal path sets function. So that is to say, if you can find a path set and all of the components in that path set are functioning, then you know that phi of x will be 1. Now when you see the words one or more functioning, you should think of a parallel system. That's how a parallel system works. You need one or more components to function. So this can be expressed more succinctly using a maximum of the alpha j of x's. But you know from up here that those alpha j of x's are simply the product, so now you have the maximum of the product of those values. And finally, you know that the maximum can be written as 1 minus the product of 1 minus the argument, and that leads you down to here, and that is a way of writing a coherent system of n components as a parallel arrangement of series subsystems. Notice that it is parallel on the outside, that's here, and it is a series subsystem on the inside, and we'll see that illustrated on the next page. Here's an example. We want to write phi of x as the parallel arrangement of S banks of series subsystems. So here is the system of interest. It's component 1 in series with the parallel subsystem 2 and 3. For this particular system, we've looked at it before. There are 2 minimal path sets. The first one is components 1 and 2, and the second minimal path set, components 1 and 3. So phi of x, using the formula on the previous slide, is 1 minus the product from j equals 1 to 2, because there are 2 minimal path sets, of 1 minus the product for I an element of pj of x sub I. When you plug in our specific P1 and P2 values, you'll notice you have a 1 minus x1, x2, that's this product right here, which corresponds to P1, times 1 minus x1, x3, that's what corresponds to P2. When you look at this structure function and write down the block diagram for it, you can see you now have repeated components, and the repeated component in this case is 1. And keep in mind, with a repeated component, these are not 2 different component ones. This is actually the very same component here and here. When one of those goes up or down, then the other one does as well. It's just a different way of writing the system. Now you could argue that we've taken something which is a nice way of writing a system and made it more complicated, and you'll see why writing it as a parallel arrangement of series subsystems is helpful a little bit later. We now take the opposite approach, and that is the minimal cut set approach. This time we let C1, C2 through CK be the K minimal cut sets. Then what we're going to do is we're going to define a beta j of x in the following fashion. We're going to let it be 1 if at least one component in the cut set C sub j is functioning and 0 otherwise. Now when you see the words at least one component functioning, that should make you think of a parallel system. And because of that, beta sub j can be written equivalently in this fashion, and what that allows you to do is have a much more compact form for beta sub j. So now we're going to write the structure function in the following fashion. The structure function will be 1 if all of the components of one or more minimal cut sets are failed. That's what is meant here. It's written out in more detail in the textbook, but that's the way to get the system to operate. Otherwise, it will be failed. Since you have for all j, that's the same as a series system, and you get this minimal quantity right there. And you know beta sub j of x is being written as a parallel arrangement here. So we take the minimum, write it as a product, we replace beta sub j with what we have up above, and you wind up this way for writing any system as a series arrangement of parallel subsystems. Here is an example. Let's say we have the bridge structure, and the cut sets are 1 and 2, 1, 3, and 5, 2, 3, and 4, and 4 and 5. So those are C1 through C4. Here is the equation for phi of x for this particular system using the equation on the previous page. And when you write this out, notice that it is the product of 4 things on the outside. So that's the series part. So we have part 1 multiplied by part 2 multiplied by part 3 multiplied by part 4. So in each one of these brackets, we're just writing down 1 minus the product of 1 minus x sub I associated with the appropriate minimal cut sets. So do you see the 1 and 2 up here? That 1 and 2 get laid out right here. You see the 1, 3, and 5, that gets laid out right here. The 2, 3, and 4 comes in right here. And finally the 4 and 5 comes in right there. So there it is, and if we were to draw the reliability block diagram for that particular structure function, that block diagram will look just like this. So this is the bridge system written as a series arrangement of parallel subsystems. And from that, it's easy to write down the structure function. It's not so easy to write the structure function when you look at that particular reliability block diagram, but much easier to write it down using that reliability block diagram. So here's the conclusion of the last few slides. For a coherent system with minimal path sets P1, P2 through PS, the structure function may be written as the parallel arrangement of S banks of series subsystems via the formula that looks this way. Notice that it is parallel on the outside and it's series on the inside. The next piece is for a coherent system with minimal cut sets C1, C2 through ck. Structure function may be written as the series arrangement of k-banks of parallel subsystems in this fashion right here. And notice that that one is series on the outside and parallel on the inside. Now there is some rather extraordinary notation. You can rewrite that previous slide, and there is this upside down pi notation. You can see it right here. And what that upside down pi notation accounts for is a parallel system. So when you have the regular product that you're used to, you are working with a series system. When you have the other upside down pi, you're working with a parallel system. And this just shows you how nicely these things work in terms of the two results. So here is the phi of x with the parallel on the outside and the series on the inside. And here is that same result with the series on the outside and then the parallel on the inside. This is some great notation that somebody invented, but it makes for a nice way of seeing the analogy between taking the minimal path vector approach and the minimal cut vector approach.